Hello, this is day 8 and we are going to start a new topic, a generative model for discrete data. So, topic is generative models for discrete data. Okay, so suppose I have one feature vector and I want to classify this using a Bayes rule. So this will be our prime objective for this topic. The generative generative classifiers, these are of the form like p y equals to c given feature vector x and model parameter theta, uh, which is proportional to probability of feature vector x. Okay, given y equals to c, the class level, and model parameter theta times p y equals to c given the model parameter theta. Fine. So I hope this formula is clear and most obvious. Okay. Uh, we already know the Bayes rule, and this is just its form. So, and this is the classifier model uh, definition. So, yeah. But before I start with this topic, I just want to say some of the basic concepts so that you can understand this thing more clearly. And these concepts are like likelihood, prior probability, posterior probability. Uh, okay, so one by one I will be discussing this concepts, right? So yeah, uh, likelihood. Okay, so the likelihood is given by probability of P given a dataset T and a hypothesis H is given by 1 by size of H times the number of events that occurred. Okay, uh, so okay, how you can understand this uh, formula? This is very simple. Uh, so this D is our given data set. For example, if our data set is like 16, this event 16 has occurred and we want to guess the hypothesis. So Uh, by looking at this number, what you can say, what can be our data set? It is just guesswork. So you may say that uh, it can be all the even numbers. Uh, okay, so you are just guessing that the data set can be 2, 4, 6 up to 98. So suppose the limitation is the data set should be less than 100. So all the numbers should be less than 100. So this is our first guess, right? We may also say that our uh, hypothesis is like uh, all to the power 2, 2n. So then according to this hypothesis, our data set will be 2, 4, 8, 16, 32, 64, only this. Okay, so yeah, and size of this hypothesis is like size of this data set. So this will be like 50 and this will be like 6. So and n says the number of occurrences. uh, Suppose for this it is only one. Suppose one more event would have occurred and that is 2, then the n would be 2. So yeah, I hope you have understand what this formula actually means. So yeah, this you can see that it is inversely proportional to size, right? So what we can say that if we will the likelihood of those hypotheses will be more which have lesser number of size. So this is having more likelihood than this. So okay, moving to next concept, that is prior probability. And yeah, this is given by p of h, probability of this hypothesis. And there is no hard and fast rule of this prior probability, but we mainly give low prior probability for unnatural concepts. By unnatural concept I mean suppose ph of even, this is natural, h to the power 1 n is natural. But if I say h to the power n except 32 or except 16, then these things are not normal, not natural, and hence we will be giving the prior probability uh, less. Okay. Uh, Now moving to posterior. So the posterior probability is nothing but a product of likelihood time times uh, which is normalized. So yeah, the formula will be p h given d So we are mainly guessing the hypothesis given the dataset is given by P D H P H by summation of all the H in hypothesis space capital H P D H bar. So yeah, this term is prior, this is likelihood, and this is the normalized version. So in other words, we can also write the above formula as P H I D belongs to H and H to the power n by summation H dash, where H bar belongs to hypothesis space capital H, P hypothesis H bar, I D belongs to H dash by H power n. Okay, so whenever our present data set and each of the element of this present data set is in this hypothesis, then this thing will be 1. For example, our hypothesis is like odd number, even number, then 2, 4, 6 up to 98, and our D is like 16 and 32. So then this will be true, and I will be this value will be 1, and hence there will be non-zero probability. But if our hypothesis is like H odd, 1, 3, 5, then this data set does not is not a subset of H odd, and hence I this will be 0. So our posterior probability will be 0, and this is like the size of this hypothesis to the number of occurrences, and this is just an uh, average normalized version, that is all the hypotheses in the H space. So yeah, this is the formula. So whenever our data is large, is huge, then the entire probability P H D, that is posterior probability, will be tending towards map based probability. Okay, so maximum up, so this is given by H map is nothing but argmax H P H D, which is nothing but posterior mode. So we will be varying H and choosing that H where this probability will be maximum, and assigning to this H bar uh, so h hat will be that h where this probability will be maximum, and then this will be replaced by here. Now we already know direct function of hxa is equals to 1 when x is in set A and equals to 0 when x is not in set A, right? Yeah, so whenever this new hypothesis is in set this hypothesis, this h, then uh, yeah, this will be 1, so the probability, posterior probability will be 1, else it will be 0. So this is map best probability. Another is MLE, like maximum likelihood estimate. uh, okay, so here h cap MLE is by definition argmax h p d h is nothing but